what are the classifications of matrix method, what is meant by flexibility matrix method, what is meant by stiffness matrix method, and what is the stiffness matrix. And last, after the end of this session, you will be able to explain the analysis of continuous beam and frame using stiffness matrix method. Why we have to select the matrix method over various methods? The main problem in the structural engineering it is we have to determine the indeterminate structures. There are various methods are available to solve the indeterminate structure. For hand correlation, the best among all the methods in this, that is like strain energy method, various methods, the best among all the methods are the Canis method. But currently we are using the multi-story building where we will be having inconvenience in finding difficulties in finding the analysis will be very complicated, so we have to go for the computer method. So we have developed a analysis method which is known as matrix method, where we can able to determine the high degree of indeterminacy. The matrix method is majorly classified into two categories. One, it is flexibility matrix method, another it is stiffness matrix method. What is meant by flexibility matrix method? The flexibility matrix method was developed from the consistent deformation method in the matrix form. This method is also known as redundant forces, where the basic unknowns will be only the redundant forces. To determine the redundant forces, we will be going for static indeterminacy. Hence, the analysis has to first find the basic determinate structure and we have to identify the redundant forces. This method is also known as flexibility method or compactability method. Now we'll start about the stiffness matrix method. The systematic development of the slope deflection method in the matrix form has given rise to stiffness matrix method. So the stiffness matrix method will be purely based on the slope deflection method, which we have already discussed in these previous sessions. This method, the basic unknowns will be the displacements of joint. The displacement means not directly the displacements alone. Here the displacement represent both slopes as well as the deflections. So what we have to do it is we have to find the equilibrium equation and we have to solve to get the slope and deflection at each and every joints. Using this method, we are going to determine the moments and shear forces using this stiffness matrix. This method is also known as displacement or equilibrium method. Now, before going for the stiffness matrix method, the main component in the stiffness matrix method is the stiffness matrix. If a structure is having n coordinates, the forces response each due to the displacement is represented in the form of K, that is nothing but the stiffness matrix. We have to determine the stiffness matrix for each and every joint by applying the displacement at each and every coordinates. The displacement can either be a slope, that is theta is equal to 1, or either it can be a displacement del is equal to 1. The element are represented as K11, K12, K1n, K21, K22, K2n, like this, where the one represent, that is the first, that is if I am taking a stiffness matrix as Kij, the Ki represent which coordinate I am taking, and the second denominator, that is the J, represent at which coordinate I am applying the unit displacement. When I am showing the problem, you can able to clearly understand, because with the figure representation it is very easy for everyone to understand. Same manner, now if you take Kii del I, means it is the force developed at coordinate I when I am applying the displacement del I at I. Similarly, Kij del J means the force developed at coordinate I due to when I am applying the displacement at del J at the J coordinates. Hence, we have to generate the jth column of the stiffness matrix, we have to apply the unit displacement in coordinate j, and we have to determine the force response for each and every coordinates due to the displacement at j column. Thus, to develop the stiffness matrix, we have to apply unit displacement in all the coordinates starting from 1 to the n. That is how many kinematic independency we are getting, that much coordinates we have to determine. And we have to determine the force developed at all the coordinates. Based upon the Maxwell theorem and similarity of matrix, if I am taking Kij, it will be equal to Kji. That is, if I am having K12, it will be equal to K21. Same manner, if I am having the matrix at K31, it will be equal to the matrix K13. Now we'll go for the equation of stiffness matrix method. In this method, the basic unknowns we have to determine will be the displacement of various joints. Hence, we have to determine the kinematic indeterminacy in order to find the coordinates. Next, we have to give the coordinate number to the unknown displacement components. Thus, the basic unknowns will be del 1, del 2, del 3 up to del n, and the displacement in coordinates directions at 1, 2, 3 up to n respectively. To start with the joint displacement in all directions, we have to consider the structure as fully restrained structure, and we have to analyze with the restrained structure only. The first we have to determine the forces. Let the forces develop due to the applied load, that is given load will be as P1, P2, P3 up to Pn. Next we have to determine the stiffness matrix of the structure by applying unit displacement at each coordinate, and we have to find the forces developed. Let K be the stiffness matrix and del be the displacement vector. Let the final forces developed be P. Then we have to form the principle of superposition and equilibrium condition to make a total equation, stiffness matrix equation. The stiffness matrix equation which formed it is because of principle of superposition and equilibrium condition is P1 is equal to P1L plus K11 del 1 up to K1N del n. Same manner we have to determine up to Pn, where the P1 represent the matrix and P1L represent the load at a coordinate, and K11 represent the displacement when applying a unit displacement at a joint 1. So if we solve this, we will be getting the matrix form as P is equal to PL plus K into del, where K into del, the same thing can be written as K into del is equal to P minus PL. If we solve the matrix stiffness equation and if we form the equation, we will get the form as Pi is equal to PAL plus summation of J is equal to 1 to N Kij del I. This method is also known as stiffness matrix method because we are using the stiffness matrix. It is known as displacement method because the basic unknowns are displacement, and it is also known as equilibrium method because the equilibrium only have to be formed and we have to solve. Now before going for the problem, let me first finalize you the step-by-step procedure to determine the stiffness matrix. The first step in this method it is what are the structure they are giving. We have to determine the kinematic indeterminacy of the structure. The kinematic indeterminacy for the structure can be determined either using the formula or either if you are very good at assigning using the support condition, we can able to assign based upon the support condition. First we'll see the different formulas for the different structures. dk is equal to 3j minus r if we are considering the rigid jointed plane frame. If I'm having a rigid jointed space frame, to determine the kinematic indeterminacy, we have to use dk is equal to 6j minus r. If I'm having a pin jointed plane frame, to determine the kinematic indeterminacy, we have to use dk is equal to 2j minus r, and for pin jointed space frame, it is 3j minus r, where j represent the number of joints and r represent the number of reaction for the given supports. Degree. Now we'll list out the degree of freedom for different support conditions. For free end, the degree of freedom is 3. That is, it can able to rotate, it can able to deflect, deflect in both x as well as in y direction. When I am considering the roller support, it can able to rotate as well as it can able to displace in x direction, that is horizontal direction. So the degree of freedom for roller end is equal to 2. When we are considering the pin jointed support, it can't able to move horizontally as well as in vertically, but it can able to rotate. So the degree of freedom for the pinned support is equal to 1, and for fixed end it can't able to rotate, it can't able to move horizontally or vertically. So the degree of kinematic independency for fixed end is equal to 0. The second step, it is how many number of kinematic independency we are getting, that much coordinates we have to assign. The so we have to assign the coordinate number to the unknown displacements. The third step, it is we have to impose the restraint structure in all the coordinate direction to make the structure as fully restrained. And we have step 4, we have to determine the forces developed in each of the coordinate direction of a fully restrained structure. It is called as PL. That is, we have to consider the total structure as restrained. For the given load condition, we have to determine the fixed end moment. The fixed end moment is only known as PL here. Here PL is not the load directly, it is the fixed end moments. Next, step 5, we have to determine the stiffness matrix by giving the unit displacement to the restraint structure in each of the coordinate direction, and we have to find the forces developed in all the coordinate direction. Here, what does it means? We have to determine the k value by applying the unit displacement in coordinates, and the remaining coordinates we have to assume as restraint. And step 6, we have to observe all the final forces in various coordinate directions. Here the final forces represent the load which is acting in the support directly. Step 7, we have to solve the stiffness equation k del is equal to p minus pl in order to get the displacement. Here the displacement means either it can be slope or either it can be del x or del y. Next, last step, we have to determine the member forces, that is the moment, using these joint displacements. Now, we'll explain you the problem for both beams as well as frame. In beams, we'll see both with the sink and without sink, as well as in frame, we'll see both with the sway and without sway. Now, the first problem, it is analyze the continuous beam shown in figure below by displacement method. We have to take EA is equal to constant throughout. Here we have to determine, first step we have to determine the kinematic indeterminacy. So I will be doing based upon the support condition. So here the A support, it is fixed. As it is fixed, we will be getting the degree of freedom as equal to 0. And in subjoint B, as it is a pin jointed support, we will be getting the kinematic indeterminacy is equal to 1, and for C we will be getting is equal to 1. Therefore the total degree of freedom for the given structure is equal to 2. Step 2, we have to assign the coordinate number to the unknown displacement. Here A, there is no kinematic indeterminacy, so there won't be any coordinates. But when it coming for B and C, we are getting 1 degree of freedom for B and 1 degree of freedom for C. So we have to assign the coordinate number for the unknown displacement, that is for the unknown kinematic indeterminacy. So when I am assigning for B, we have to assign 1 coordinate, for C we have to assign 1 coordinate. Next, we have to make the structure as fully restrained structure. So how we can able to make the structure as restrained? The only form to make the structure is restrained, it is in order to form a fixed n at all the joints. So we have to give a fixed joint at both fixed n at both the joints B and C. Then we have to step 4, we have to determine the PL value. The PL value P value, the P value can be developed in the coordinate direction of a fully restrained structure. So we have to consider the structure as fully restrained and we have to apply the load, and I think you may already know the formulas for fixed end moment for both for all the load conditions. For UDL, it is W L square by 12, and for point load, it is W L by 8. For the given structure, by considering the fixed end moment and determining the fixed end moment value, it is equal to, first, when I am considering MFAB, the fixed end moment value is equal to minus WL square divided by 12. So here the load is equal to 60 and the length is equal to 4. So you will be getting minus 80 kilonewton meter. Same manner when we are considering for MFBA, we will be getting plus WL square divided by 12, where load is equal to 60. It is 60 into 4 square divided by 12, which we will be getting as 80 kilonewton meter. Next, when we are considering MFBC, it is minus WL by 8, where the load is equal to 100 kilonewton, the length is equal to 3, and by 8. It is why it is equal to WL by 8. It is the load is acting perfectly at the center WL by 2, sorry, L by 2 distance. So only we are using WL by 8. Otherwise, we will be getting WA square B by L square and WAB square by L square. As the load is acting perfectly at the midspan, we have to use the formula is minus WL by 8, where load is equal to 100 kilonewton and length is equal to 3 meter. We will be getting minus 37.5 kilonewton meter for MFBC, and for MFCB as plus 37.5 kilonewton meter. Next, what we have to do it is we have to take the joint and we have to consider the total fixed end moment at a joint. So here the we are assigned the coordinate, first coordinate as B and the second coordinate as C. When we are assigning the first coordinate at B, there are two members fixed end moments we will be having. One it is MFBA, another one it is MFBC. So we have to add both the member fixed end moments. So the P1L is equal to MFBA plus MFBC, where we will be getting 42.5. Same manner, when we are assigning for P2L, we will be having only one member at the joint C, which is nothing but MFCB. So we can able to directly take the value and we can able to form the matrix as PL is equal to 42.5 and 37.5. And the next step, where we have to determine the stiffness matrix. The stiffness matrix is assembled by slope deflection equation. You already know the slope deflection equation. The formula, the slope deflection equation for the stiffness, it is equal to 2EI by L, 2 theta A plus theta B minus 3 del by L. We are going to use that equation and we are going to determine the stiffness matrix. First, we have to assign the unit displacement or unit rotation for the unknown coordinates. First, we have to apply the unit coordinate displacement at coordinate 1, and we have to determine the stiffness matrix at both coordinate 1 and coordinate 2 due to the unit displacement at coordinate 1. I am repeating again. First, we have to determine the stiffness matrix for at a coordinate by applying a unit displacement at coordinate direction 1. It will be K11 and K21, where K1, the one represents where we are taking the coordinate, and the second digit represent at which coordinate we are applying the unit displacement. So first what we have to do it is we have to apply a 1 radian rotation at coordinate 1, that is at B, and we have to determine the stiffness matrix for coordinate 1 and coordinate 2. So the coordinate 1, when I am taking coordinate 1, I am having two members, that is BA as well as BC. So I have to determine the stiffness equation for both BA as well as BC. Here K11 is equal to, you can able to see I have taken both coordinate, that is both the members, that is BA as well as BC. So the equation will be formed in the manner as 2EI by L 2 theta b plus theta a minus 3 del by L. As there is no displacement del value, it will be considered as 0. The second, it is 2 ei by L 2 theta b plus theta c. As we are considering the member BC, it is B and C. And the total stiffness value is equal to 7 ei by 3. Next, we have to determine the stiffness matrix at K21. When we are considering the K21, it is nothing but the member CB. So it will be 2 ei by L, 2 theta C plus theta B minus 3 del by L, where we are applying the unit displacement at coordinate 1, that is theta b is equal to 1. The remaining ends will be considered as fixed, so the theta a value will be equal to 0 and theta c value will be equal to 0. Substituting these values, we will be getting K21 is equal to 2 ei by 3. Next, same manner, we have to now consider apply the unit rotation at coordinate direction 2. If I am applying the unit displacement at coordinate direction 2, here it will be allowing the rotation, but the other structure has to be considered as restraint. So when we are applying the unit displacement, that is unit rotation here, theta is equal to 1. Because of this rotation, the it will be bending up to the joint B. As the joint B is already fixed, it won't allow the rotation further behind joint B. The B joint itself will be opposing the rotation. So we have to go for the stiffness matrix, where here K12, the K1, the 1 represent at which coordinate we are determining the stiffness matrix, and 2 represent at which coordinate we are applying the unit rotation. So K12 means the stiffness value at coordinate 1 when I am applying a unit rotation at coordinate 2. Same manner here, K22 means the stiffness matrix at coordinate 2 when I am applying the unit rotation at coordinate 2. So here, when we are considering K12, we will be having only theta. We will be considering both theta A and theta B, that is both the members BA and BC. But the problem it is, as B also, theta B also will be 0, theta A also is 0, we won't get any values. So I have omitted that value and we have considered only the BC value. As due to the similarity matrix, K21 will be equal to K12. If you don't have time, you no need to find K12 separately. You can directly write the value of K21 because of the similarity matrix. So you can able to find K12 and K21 value will be same. Now after determining this, we have to go for the final forces in coordinate direction. So the final forces will be considered at a joint. If there are any load, we will be considering as final forces, or otherwise when we are having a cantilever support at the corner, instead of that member, we will be considering that as a moment, and we will be considering that moment as final forces. As in the given problem, we are not having any load at the joint particularly, here the final forces value will be equal to 0. Step 7, now we have to solve the stiffness equation. The stiffness equation is K into del is equal to P minus PL. Here K matrix is nothing but what we have determined here. From here we have to take the values as in the matrix form as K11, K12, K21, K22 as 2 cross 2 matrix, and we have to form the stiffness matrix. And del value is here del 1 and del 2 represent the unknown displacement. The unknown displacements are theta b and theta c, and P minus PL, as the P values are 0 and PL values are already determined by determining the fixed end moments. Solving this, so we have to find the displacement only. So leaving the displacement alone in left hand side and moving all the others remaining in right hand side, we will be getting 3 by EI into inverse of matrix, we have to determine the matrix inverse. The inverse of matrix is nothing but 1 by modulus of A inverse is equal to 1 by modulus of A into adjoint of A. Here modulus represent 7 into 4 minus 2 into 2, and the adjoint is nothing but, for 2 cross 2 matrix it is very easy. We can able to shift this 4 here and 7 at the bottom, and we can able to add, multiply this 2 digit with minus, we will be getting the A inverse value. After this we can able to determine the theta b and theta c value. Here theta b value is equal to minus 11.875 divided by EI, and theta c value is equal to minus 22.188 divided by EI, and theta a value is equal to 0 because the theta, that is the end of A, it is already fixed. We won't get any theta values. Now by forming the slope deflection equation, we have to determine the member forces, that is the moments. So the slope deflection equation is MAB is equal to MFAB plus 2 EI by L, 2 theta A plus theta B minus 3 del by L. As the theta A value is equal to 0 and theta B value is there, substituting the theta B value, we will be getting MAB. Here MFAB represent the fixed end moment. We have already determined the fixed end moment, so we have to apply the fixed end moment value here, and the final value is the final moment for the number MAB. MBA is equal to 80 plus, that is MFBA plus 2 EI by L, 2 theta B plus theta A minus 3 del by L. So as it is 2 theta B, we have multiplied 2 into theta B value. So as like that, MBC means MFBC plus 2 EI by L, 2 theta B plus theta C minus 3 del by L. Same manner for MCB, it is MFCB plus 2 EI by L, 2 theta C plus theta B minus 3 del by L. Substituting the values, we will be able to determine the moment values directly. Now we'll tell how to draw the bending moment diagram for the given structure. I have assumed the rotation of clockwise as positive and anti-clockwise as negative. So here in this direction it will be anti-clockwise. If anti-clockwise means top it is positive, top it is negative, bottom it is positive. Here, as my assumption it is clockwise is positive, we can able to see clockwise upwards, so positive at the top and negative means downward. Same manner here, it is anti-clockwise, that is anti-clockwise I have considered negative. So if it is anti-clockwise means top it is negative, bottom it is positive, and here same manner, top it is positive and bottom it is negative. Considering this and determining the values, first you can able to see here MAB is equal to minus 85.938. According to here, if negative means it is upwards, so I have drawn this at the upward direction. Next, MBA, it is positive. Here MBA member, if it is positive it is upwards. Same manner for MBC, if it is upward it is negative, at top it is negative, so it is upwards. Next for MCB, it is equal to 0 as the corner end it is pinned end support. And for drawing the bending moment diagram, we also require the moment for the given load condition, as we are considering the simply supported end. If we are considering the simply supported end, first it is a UDL, it is W L square divided by 8. So it is, for the given load condition we have to determine by using WL square by 8, and we have to know if it is UDL, the diagram will be in parabolic shape. As it is the point load, the diagram will be in triangular shape. So for point load it is W L by 4 if it is acting perfectly at the midspan. Doing this one, we can able to draw the bending moment diagram. Sir, if anybody is having doubt in bending moment diagram, they can ask right now, sir. Hello, sir. Hello, sir. Anybody having bending moment diagram? Any doubt in bending moment diagram, you can ask. Is it audible?
Yes, sir.
Sir, if anybody is having doubt in bending moment diagram, they can ask right now, sir.
If you have any doubt, please text in the chat box. So you carry on, sir.
Okay, sir. Next, we will be seeing the frames without sway because both the beam as well as the frame will be looking similar without any sway. If there is any sway, if there is not having any sway, both the beam as well as the frame, the analysis will be looking similar. So only after the beam I placed the frame without sway. Same manner we have to determine the degree of freedom. The degree of freedom for the given structure it is, as there is a support here, it won't allow the structure to move anywhere, there won't be any sway. So here the possibility is only the rotation at joint B and the rotation at joint C as well as the rotation at joint E. So the number of degree of freedom for the given structure is equal to 3. Next we have to assign the coordinate numbers. So as I told, the coordinate number here, the coordinates will be rotation at joint B, rotation at joint C, and rotation at joint E. Therefore, the coordinates are 1, 2, and 3. All the coordinates are only in rotation direction. Then we have to make the structure as fully restrained structure. So making the structure fully restrained and by assigning the coordinates, this is how the coordinates will look. The coordinates will be looking in this manner, that coordinate 1 in rotation direction, coordinate 2 in rotation, and coordinate 3 in rotation. And this is the fully restrained structure. After making the structure as fully restrained, we have to determine the fixed end moment value for determining the force developed in each of the coordinate direction. Here the MAB will be equal to 0, as there is, if you see the question, we are having load in only one end, which is nothing but at the member BC. So we'll be getting the fixed end moment values only in MFBC and MFCB, and remaining all the members, the fixed end moment value will be equal to 0. Here the load is, given load it is UDL, therefore it is minus W L square divided by 12 for MFBC, and for MFCB it is plus W L square divided by 12. So determining the value, we will be getting MFBC is equal to minus 120 kilonewton meter and MFCB as plus 120 kilonewton meter. We have to form the PL value. When we are forming the PL value, we have to consider the coordinates 1. When I am considering the coordinate 1, the PL value will be MFAB plus MFBC, and for coordinate 2 it will be MFCB plus MFCD plus MFCE, and coordinate 3 it will be MFEC alone. If we solve, we will be getting the PL value as minus 120 plus 120 and 0. And the next step it is, we have to determine the stiffness matrix. The stiffness matrix, as I already told in the previous problem, we have to apply the unit displacement at each and every coordinates, and we have to determine the stiffness coefficient for the all the coordinates. Here first we have to apply the unit displacement in coordinate direction 1. By applying the unit displacement at coordinate direction 1, the coordinates, the stiffness for the all the matrix will be K11 K21 and K31. Here K11 represent the one represent at which coordinate I am determining the value, and the second, this one represent and which coordinate I am applying the unit displacement. Here the one represent which coordinate I am considering, and the second one represent at which coordinate I am applying the unit displacement. As it is coordinate 1, it is k11, and the second coordinate it is k21, means where 2 represent the coordinate number and the 1 represent at which coordinate I am applying the unit displacement. Same manner at the last, for third coordinate it is k31, where the 3 represent the unit the coordinate and 1 represent which where I am applying the unit displacement. By applying the unit displacement, we will be getting same slope deflection equation for the stiffness. It is equal to K is equal to 2 EI by L 2 theta B plus theta C, sorry, 2 theta B plus theta A minus 3 del by L. As there is no deflection, that is del values, we have to consider the values like this. For it is for the member M B A, and this is for the member M B C. The summation of these both the members will leads to the value of K11. Next, K21, as I already told, based upon the similarity matrix, K21 will be equal to K12. Here in K2 we are having 3 members, so we have to consider all the 3 members. 3 members are M, CB, M, CD, and last M, CE. Summation of these 3 stiffness, we will be getting the value of K12, K21 and K12. Next we have to go for last member K31, that is this value. As both the ends are fixed, we are not going to get any values, that is theta value of C, theta C value will be equal to 0, theta E value equal to 0, and theta D value will be also will be equal to 0. Here we will be getting theta B value alone equal to 1. All the remaining supports, as it is fully fixed, we will be getting theta A, theta C, theta D, theta E is equal to 0. By applying the values of thetas, we will be getting K21, K12 is equal to EI by 3, and K31, K13, we will be getting the value as 0. Next, we have to apply the unit displacement in coordinate direction 2. By applying the unit displacement in coordinate direction 2, here at coordinate 1, here K12 represent at coordinate 1 stiffness of coordinate 1, while I am applying the unit rotation at coordinate 2. Same manner K22 and K32 respectively. Here, as I am applying the unit rotation here, we will be getting here also slope like this. So the values here, the theta, here the theta A value will be equal to 0, theta B value will be equal to 0, theta D value will be equal to 0, and theta E value will be equal to 0. As here I am applying rotation, it will allow the rotation at member for BC, CE and CD. The total, as we already told, we have determined the K21. K21 is equal to K12, so we no need to find the K12 value again. We can able to directly determine the value of K22 by applying the slope deflection equation 2EI by L 2 theta C plus theta B, same manner for all the members. Next we have to determine the K32 or K23 both are equal because of the similarity matrix. K32 will be equal to K23. So here it is 2 EI by L 2 theta A, sorry, 2 theta E plus theta C minus 3 del by L. Applying the value of theta C is equal to 1, we will be getting 4 EI by 9. Next, by applying the unit displacement in coordinate direction 3, when we are applying the unit displacement in coordinate direction 3, here the stiffness matrices will be K13, K23 and K33. As we have already determined the K31 value, it will be equal to K13. As we have already determined the value of K32, which will be equal to K23, we need to only determine the value of K33 alone, where by applying the unit rotation at 3, we can able to directly determine the value of 2 EI by L, 2 theta E plus theta C minus 3 del by L. We will be getting the K33 value is equal to 8 EI by 9. Next, we have to determine the final forces. As there are no loads in a joint, we will be getting the final forces P value equal to 0. By solving the stiffness equation, we will be getting K into del is equal to P minus PL. By substituting the values of K value, del value and P minus PL value, we will be getting the matrix form like this. When we are making this, keeping the del, that is deflection alone in the left hand side and moving all the remaining portions in the right hand side, we will be getting the inverse of the matrix. The inverse of the matrix for 3 cross 3 matrix is equal to A inverse is equal to 1 by modulus of A into adjoint of A. Now I will clearly explain you how to determine the inverse matrix for the 3 cross 3 matrix. For determining the 3 cross 3 matrix, first we have to consider modulus of A. When we are taking modulus of A, we have to close these values first, that by keeping multiplying, and we have to we have to determine the value by multiplying, cross multiplying like this. So here we have to keep 12 into 20 into 8 minus 4 into 4. When we are taking the modulus of A for 3 cross 3 matrix, first it is positive, second we have to consider as negative, third we have to consider as positive. So here first one it is 12 into 20 into 8 minus 4 into 4. Next, minus 3 into, when we are considering this matrix, we have to consider 3 into 8 minus 4 into 0, and last it is 0. So it is 0 into the remaining value will be equal to 0. Next, when we are considering the inside values, when we are considering the first matrix, we have to close these values. So which is nothing but 20 into 8 minus 4 into 4, which will be giving you 144. Here also we have to consider plus, minus, plus, minus, plus, minus, and plus, minus, plus. This is how we have to form. When we are considering, when we are going for the first matrix, we have to close the first matrix and we have to cross multiply this one. When we are going for the next one, that is here, we have to close this value and we have to multiply 3 into 8 minus 0 into 4. Next, for last one, we have to close these values and we have to multiply 3 into 4 minus 20 into 0. So we will be getting the values like this. Next, for second matrix, here we have to close this one. For second one, we have to close this one. Sorry, for second matrix, we have to close the second one here and here. We have to cross multiply 3 into 8 minus 4 into 0. Same manner, when I am considering here, I have to close second matrix of both second matrix as well as the first second column, we will be getting 12 into 8 minus 0 into 0. 12 into 8 is equal to 96. Here first one it is negative, second one it is positive, third one it is negative. Same manner we have to do, and we have to determine the transfers, as due to the similarity matrix we will be having both the values, this one as well as this one will be same. So even if you are transferring, the values will be similar only. Then we have to determine the theta, the deflection value, del value. Here del 1, del 2, del 3 all are representing the rotation, that is theta b, theta c and theta e. So by using this equation we can able to determine the value of theta b, theta c and theta e. After determining the value, we have to go for determining the member forces. The member forces formula, it is using the slope deflection equation, it is m ab is equal to m of ab plus 2 ei by l, 2 theta a plus theta b minus 3 del by l. By using the value, we will be able to determine the mab value. Same manner, we can able to apply the slope deflection equation for the given members for all the members, and we have to determine the final end moment values. Sir, whether they want me to explain the bending moment diagram for the frame or not, sir? Hello, sir.
Sir, if they have any doubts, na, they type in the text box, sir. I will deliver, sir. You can continue, sir.
Sir, can I just a minute? Can I have some water, sir?
Okay, sir. Okay, sir.
Okay, sir. For drawing the bending moment diagram, we have to consider the rotations. I'll be drawing the rotation alone, where we can able to determine by using the clock whether clockwise will be positive or anti-clockwise will be positive. So here, for my assumption, it is clockwise. It is positive. So here, if I am considering anti-clockwise, here it is negative. Here it will be positive. Same manner, if it is positive here, negative here, or here, negative at the top, positive at the bottom. Here it is positive at the top, negative at the bottom. Here, negative here, positive here, and negative here, positive here. So based upon what are the moment values we are getting, we can able to draw the bending moment diagram. Next problem, it is analysis of the continuous beam with a sink. That is, if the support B is sinking by 10 mm and they have given the value of EI value, we have to determine the moment. We have to analyze the continuous beam using stiffness matrix method. Here, the first step, we have to determine the kinematic independency. Here, the kinematic independency is nothing but here the rotation 1, here also rotation 1. Therefore, the total degree of kinematic independency for the given structure is equal to 2. Step 2, we have to assign the coordinates. The coordinates assigned is at joint B it is rotation, at joint C it is rotation, and next we have to make the structure as fully restrained structure. As there is no loads, we can able to make the structure fully restrained, and we have to determine the forces developed in each of the coordinate direction. If there is any sink here, the rotation will be in this manner. If we consider, we can able to see because of the sink in the left hand side it is in anti-clockwise direction because of the sink, and in right hand side it will be in clockwise directions. The rotation will be in clockwise direction, which represent the left hand side members, that is MBA and BMB, MAB and MBA will be considered as negative, and MBC and MCB will be considered as positive. Here, the formula for determining the fixed end moment, if there is any load, we have to consider the fixed end moment for the given load condition also. As there are no load in the given question, the here we are not considering the loads, we are considering only the settlement. The formula for settlement, it is 6 EI del by L square. As I told here, as the my assumption it is clockwise, it is positive. So at MAB and MBA the settlements are in anti-clockwise direction, so it is negative. The formula for settlement, it is minus 6 EI del by L square. So here we are considering negative. The settlement is 10 mm. When we are converting to meter, we will be getting 0.01 meter. So solving this one, we will be getting MFAB value is equal to minus 80, MFBA as minus 80, MFBC as plus 56.25, and MFCB as plus 56.25, because MFAB and MFB are in anti-clockwise direction and MFBC and MFCB are in clockwise direction. So considering the coordinates 1 and coordinate 2, that is joint B and joint C. At joint B, we are having two members, that is MFBA and MFBC, and at joint C, we are having only one, which is nothing but MFCB alone. Solving this in matrix form, we will be getting the PL value. After determining the PL value, we have to go for the stiffness matrix method by applying the unit displacement in coordinate directions. When we are applying the unit displacement in coordinate direction 1, we will be getting the value as coordinate direction at 1. The value will be K, the stiffness coefficient will be K11 and K21. Solving this one, we will be getting K11 is equal to 5.167 EI and K21 will be equal to 1.25 EI. Next, we have to solve by applying the unit displacement in coordinate direction 2. Whenever we are applying a unit displacement in a coordinate, all other joint should be considered as fixed end only. Then only we have to apply the unit displacement. When I am applying the unit displacement at coordinate C, the stiffness coefficient will be K12 and K22. Applying the value, K12 will be equal to 1.25 EA and K22 will be equal to 5 EA. Here, the final forces in all the coordinate direction, P value will be equal to 0, as there is no load in the any joints. Next, we have to determine the stiffness equation. The stiffness equation, the unknowns are theta B and theta C. By determining the theta B and theta C, we have to determine the final moment member forces. Here we have to be very careful that is there any sink, as there is sink here del value, why can't we consider that del value here? Here the del value should be here the value should be considered only from the unknowns of kinematic indeterminacy from here only. We should not consider the value of del here. If you are having any, that is if you are having del value here only, we can able to substitute that value here, and we can able to determine what are the unknown displacement we are getting here only, we have to substitute here. Therefore here the 3 del by L, here the del value will be equal to 0 only. Determining the final n moments, we have to solve the problem and we have to get the value of all the final moment values. Here MAB is equal to minus 69.613, MBA is equal to minus 59.227, MBC is equal to 59.227, and MCB is equal to 33.33 kilonewton meter. So getting solving the formula, and if we are drawing the bending moment diagram, the bending moment diagram will be looking like this only. Next we have to determine, we have next problem is the frame with the sway. Here you can able to see here a load is acting horizontally at a joint which leads to the sway like this, which lead to the sway of the structure like this. So we have to analyze this frame with the sway. So now the step one, we have to determine the degree of freedom. The for the given question, the degree of freedom, or for the given problem, the degree of freedom will be here one at coordinate. We have to consider one horizontal, 1 degree of freedom is there, and rotation at joint B and rotation at joint C. Therefore, the degree of freedom for the given structure is equal to 3. Step 2, we have to assign the coordinate for the given structure. By assigning the coordinate, we will be getting one horizontal displacement, second rotation, and third rotation. And after determining this one, we have to determine the fixed moment values for determining the PL values. The fixed moment for the given load condition, it is equal to, as it is a UDL, it is minus WL square by 12 and plus WL square by 12. Substituting the values, we will be getting MFBC as minus 40 kilonewton meter and MFCB as plus 40 kilonewton meter. This is the PL value. Next, we have to determine the stiffness matrix. For applying, first we have to apply the unit displacement at coordinate 1. When we are applying an unit displacement at coordinate 1, the stiffness coefficient value because of this displacement is, for rotation it will be 6 EI del by L square, and for displacement it will be 12 EI del by L cube. I am repeating again, because of the displacement, the stiffness coefficient value for displacement will be 12 EI del by L cube, and for rotation it will be 6 EI del by L square. Here K11 represent the displacements, so we have to consider the displacement stiffness coefficient values, and K21 and K31 represent the rotation, so we have to consider the rotation values. Here the rotations are in anti-clockwise direction, so we have to consider as negative values. So the K11 value will be equal to 12 EI del by L cube plus, 12 EI del, here del value is equal to 1, so it will be 12 EI by 4 cube plus 12 EI by 2 cube, and for K21 and K31 it is K21 at joint B. Here the total span it is equal to 4 meters, so we will be considering 6 EI by 4 square. K31 it is 6 EI by 2 square. Next, we have to apply the unit rotation at direction 2, because the second coordinate is nothing but a unit rotation. So we have to apply the unit rotation at coordinate direction 2, and we have to determine the value. Already we have determined the K21 value, so it will be equal to K12. So we no need to determine the K12 value once again. Next, we have to determine the K22. We already know the formula for stiffness. It is 2 EI by L, 2 theta A plus theta B minus 3 del by L. Here we are not having any deflection at when we are applying unit rotation. So we have to consider K22 only for BA as well as BC, and for K32 we have to consider CB. By substituting the values, we will be getting K22 is equal to 2 EI and K32 is equal to 0.5 EI. Next, we have to determine the unit displacement in coordinate direction 3. The unit displacement at coordinate direction 3 means by applying a unit displacement at coordinate 3 and determine the remaining coordinates. K33 value will be equal to, as we already determined the value of K32, that value will be equal to K23. So we no need to determine the value of K23 again. We can directly write the value of K33, which is equal to 3 EI. Next, we have to determine the final forces. Till now, for the previous three problems, we did not have any forces at a joint. So we have considered that force value is equal to 0. But in this problem, in the question, we are having at the coordinate direction 1, we are having a load at the joint which is equal to 50 kilonewton, which is acting from left side to right side. Based on our assumption, left side to right side it is positive. We will be considering that value of P as 50, and we are not having any other rotation for coordinate 2 and coordinate 3. So it is 0 and 0, as we are having only one value, that is we are having only displacement direction, we are having only one load which is 50 kilonewton. We have to consider that value 50 kilonewton here. Therefore the P value will be equal to 50, 0, 0. Next we have to determine the displacement, that is del theta theta b and theta c by using the stiffness equation. By solving the stiffness equation, we will be getting the del 1 value as 35.556 divided by EI, theta b is 26.667 divided by EI, and theta c as 0. Solving this in final moment values, I have to mention one point here. For the given problem, we are having the sway, because of the sway there will be changes only in the AB and CD member. Even there is sway, there won't be any change in geometry of BC. There won't be any change in geometry of BC. Therefore we have to consider the del value for the BC member and CB member as 0. We have to consider only the del value for AB member and CD member alone. So by considering the del value for only AB member and CD member, we will be getting here 3 into del by L. So here we will be getting 3 into 35.556 divided by 4 EI. Substituting the value of del theta B and theta C, we will be getting the final member forces for all the members as MAB is equal to 0, MBA is equal to 13.333, MBC is equal to minus 13.333, MCB as 53.333, MCD as minus 53.333, and MDC is equal to 0. This is the final bending moment diagram for the given frame structure for the value which we have determined. Here minus, plus, plus, minus, minus, plus, plus, minus, plus, minus, and minus, plus. Based upon the rotation, this is how, if it is positive we have to move in this direction, if it is negative we have to move in this direction. And final problem, it is analysis of beam. Here the difference it is, we are having a cantilever beam, we are having a cantilever, that is overhanging beam at this portion. If there is overhanging beam, what we have to do? The first step we have to determine, we have to consider this, because of this overhanging beam there won't be any change in the structure. So what we have to do it is, instead of this overhanging beam, we have to consider that overhanging beam as a moment. How we can able to consider this overhanging beam as a moment? So the moment, how we can able to convert load into distance will give us a moment. Here the load is 60 and the distance is 2. We will be getting the moment as 120 kilonewton meter. 16 to 2 is equal to 120 kilonewton meter. So we have to eliminate this member by applying, by converting that load cantilever portion into a moment value as 120 kilonewton meter, and we can able to eliminate this member CD itself. After eliminating, the structure will be looking like this only. So instead of CD, we have made that CD portion as a moment of 120 kilonewton meter. Step 1, same manner, we have to determine the kinematic indeterminacy. For the given structure, the kinematic indeterminacy will be equal to 2, which is nothing but at joint B 1 rotation, at joint C 1 rotation. Step 2, we have to select the coordinates. The coordinates has to be selected. Step 3, we have to make the structure as fully restrained structure. Making the structure fully restrained, it will be looking like this only. Next, we have to determine the forces developed in each of the coordinates by using the fixed end moment formula. Here it is at joint AB, it is at a distance of AB. So we have to consider as W AB square by L square and W A square B by L square value. For AB it is W AB square by L square, and for BA it is W A square B by L square. And for joint BC it is UDL, it is minus WL square by 12, and for joint CB it is plus WL square by 12. By considering this value, for at joint B we are having BA and BC, so we have to consider BA and BC, and for joint C we are having only CB, we have to consider only CB alone. Next, we have to determine the stiffness matrix for the given question by applying the unit coordinate direction. By applying the unit displacement in coordinate direction 1, we will be getting the diagram like this, as A and C only fixed. When we are applying a unit rotation at joint B, it can able to rotate up to A as well as it can able to rotate up to C. By determining the values of K11, we can, by applying the unit displacement by using the slope deflection equation as 2ei by L, 2 theta A minus theta B, 2 theta A plus theta B minus 3 del by L, we will be determining the value of K11 and K21. K11 means we have to consider slope deflection equation for stiffness for both BA as well as BC, and for joint C we have to determine only for CB alone. Here the theta A value will be equal to 0, theta C value will be equal to 0, and theta B value will be only equal to 1. Next, we have to determine the unit displacement at coordinate direction 2. By how we have to determine the unit displacement at coordinate direction 2, it is we have to apply a unit rotation at the coordinate 2 alone. When I am applying the coordinate at 2, we have to consider all other joint as 0. By applying all other joint as 0, we will be getting theta A value will be equal to 0, theta B value will be equal to 0, and we will be having theta C value alone, where theta C value will be equal to 1. By applying the slope deflection equation for stiffness, we can able to determine the value of K22, which is equal to EI. Next, we have to determine, before determining the stiffness equation, we have to determine the value of P, that is the final load value. The final load value will be equal to 0 and 120. How 120 came? Because at joint C, instead of CD, we made the structure as a unit moment, which is nothing but 120 kilonewton meter. that 120 kilonewton meter at joint C, that is coordinate 2, we have to take that value as P value. At coordinate 1, we are not having any loads at joint, so it will be equal to 0. Next, we have to determine the stiffness equation. The stiffness equation is equal to K into del is equal to P minus PL, where K value is equal to 7 EI by L, 0.5 EI, 0.5 EI and EI, then P minus PL value. By using this stiffness equation, we have to determine the unknown displacement, that is theta B and theta C. By using this matrix method, the theta B value will be equal to 28.802 divided by EI, and theta C value will be equal to minus 1.070 divided by EI. After determining the theta B and theta C, using the slope deflection equation, MAB is equal to 2 MFAB, that is fixed end moment, plus 2 EI by L, 2 theta A plus theta B minus 3 del by L. As del value is equal to 0, by applying the theta B value alone, that is theta A will be equal to 0 as the end is fixed. We have to determine the stiffness, we have to determine the final end moment for the all the members by applying the unit, by applying theta B and theta C value. Sir,
So thank you, sir.
sorry, sir.
Participants,
Sir, if any queries they can ask. The time more than almost 13 minutes are there, sir.
we have a lot of time. If you have any queries, please ask. Participants, please ask any questions. Okay, sir, we will wind up, sir.
Sorry, sir. I didn't manage the time.
Okay, sir, no problem, sir.
Even I try to take all the 5 problems,
So
all the
you,
methods.
so you have explained very well, sir. Thank you for your valuable time, sir.
Okay, sir.
Thank you, participants. The feedback link will be sent through your mail. Please submit your feedbacks. Hope possibly you will receive your certificate on Monday. Thank you for your registration and active participation throughout this week. Once again, thank you all, and I thank our management, principal, vice principal, dean of academics for their support, and I would like to thank our HOD ma'am for their cooperation, and I would like to thank all the faculty members of our department for their support. Thank you again. Thank you, sir.
Thank you, sir, for giving me the opportunity, sir.
Thank you, sir.
Thanks.